Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.
Hello everyone, welcome to this video. In this video, we are going to continue talking about current electricity. So in this lecture, we are going to first talk about electrical energy, power, and then we are going to talk about combinations of resistors in series and in parallel combination. Then we will talk about electrical cells, electromotive force and internal resistance. Then we will talk about the electrical cells kept in series and parallel combination. Then we'll talk about Kirchhoff's rules and how to use Kirchhoff's rules in Wheatstone bridge, meter bridge and potentiometer. So let's get into the first topic, electrical energy and power. So let's assume that there is a conductor called AB. So let's assume that this is a conductor and let's call it AB. This is just a current carrying wire. So one end of the conductor has a potential of V of A and the other end has a potential of V of B. So the difference between these two is supposed to be V of A minus V of B, which is greater than 0 because we are assuming that VA is at higher potential compared to VB. Now, the current is now flowing, so the charges are going from A to B. So in a time interval delta t, an amount of charge delta q, which is I multiplied by delta t, travels from A to B. So the potential energy of the charge at A is q multiplied by V of A and the potential energy of the charge at B is q multiplied by V of B. So we talked about the potential difference between the ends of the conductor. Now we are going to look at it from the charge's point of view. So when a charge is at a point A, its potential is q into V of A. When the same charge is at B, its potential is q multiplied by V of B. Now the change in the potential energy of this charge when it goes from A to B is nothing but the final potential energy minus the initial potential energy. So from by coming from A to B, the charge is going from one potential energy to another potential energy. So the difference in potential energy delta U is given as final potential energy minus initial potential energy. So we can take delta Q as common. So then we have V of B minus V of A. And we know that V of A is greater than V of B. So this quantity has to be negative and we denote this quantity as V. So then we get delta U potential is equal to minus delta Q multiplied by V. And now what is delta Q? In a steady current I, delta Q is nothing but I delta T. So then we will substitute for delta Q here. So the difference in potential energy when a charge goes from a point A to B is nothing but minus IV delta T, and it is obviously less than 0 because of this negative sign. So we all know that energy is conserved. So when there is a change in the potential energy, there has to be an equal and opposite change in the kinetic energy so that the total energy is conserved. So in other words, delta Q plus delta K has to be equal to 0 in an isolated system. That is the conservation of energy. So if delta U is decreasing by this amount, that means the potential energy is decreasing by this amount. That also means the kinetic energy has to increase by the same amount. Since the total energy is conserved, we are ignoring the collisions present between the electrons and between the atoms. So now the delta K becomes minus of delta U. Then we will substitute delta U value here. So delta K becomes IV delta T, which is greater than 0. That means that this quantity is increasing, the K is increasing, kinetic energy is increasing. So in this case, what we learned is when a charge goes from point A to B in a conductor, If the charge is losing potential energy, that means the charge is gaining kinetic energy. So this electron is gaining some energy. So where is this energy going? Okay. So the kinetic energy of the electrons increases as they move through the conductor, right? So where is this energy going? This excess energy is transferred to the atoms via collisions. We already talked about these collisions in when we studied the resistance. When the electrons are moving inside the conductor, they collide with the atoms because the atoms are simply sitting inside the conductors. The electrons are moving randomly. So then they collide with the atoms. So when electron with a high kinetic energy, high velocity, it collides with an atom that is simply sitting there, or relatively it is at rest compared to the electron. The electron transfers some of its energy to the atom through these collisions. So the atoms gain this energy and the atoms start vibrating more rigorously. This just means that the vibrational energy of the atoms increases as it gains some energy from the electrons. So when the atoms vibrate, what happens? The conductor as a whole heats up because it is not just one atom. There are a lot of atoms, so they start vibrating. So the conductor as a whole heats up. So this heat energy is particularly coming from these electrons. And now this heat is actually wasted. So that's why we call this heat dissipation. Because if you look at a current carrying wire, there is always some amount of heat that is wasted in the current carrying wire. And it is unwanted heat dissipation. So this dissipation is called, so the amount of energy that is dissipated as heat in the time interval delta t is delta W equal to IV delta T. Now we know that power is equal to delta W by delta T. So then power equal to I multiplied by V. So why this delta W is IV delta T? Because this is the increase in the kinetic energy that gets transferred to the atom. So the same amount is only the power dissipation. So P equals to IV, and let's substitute Ohm's law here. So we get P equals to, instead of V we will substitute IR, then we get I square R. Instead of I, if you substitute V by R, then you get V square by R. So this is the power. So this power, where does this power come from? So if you have a conductor like this where current is passing, I amount of current is passing through the resistor, and this conductor heats up, so this power dissipation happens, and this energy dissipation is coming, this power is coming from this electric cell. So this cell is only driving this current. So this cell is making the electrons go through the circuit. So by doing this cell is only supplying the kinetic energy to the electrons, and that kinetic energy gets transferred into heat dissipation. So this chemical energy of the cell only gives this power to the conductor. Okay, so we have talked about resistance in the previous lectures. So we now have an idea about what is resistance, what is resistivity, and how it is related to the drift velocity and the mass of the electrons. So we got a closer look at resistance, how resistance works and all. Now we know what is a resistor, and now we are going to see what happens if you have a combinations of resistors. For example, in this case we have series combination. So we are just keeping the resistors one by one after the other. So we are joining the end of one resistor to the beginning of other resistor. So this is called a series combination. So when we connect this series combination to a battery or a cell, then a current I passes through this. So according to charge conservation, whatever current goes through this resistor is supposed to come out of here, because there is no other branches here. So whatever charge goes in has to come out. So now we can assume that the current that is flowing through R1 is equal to the current that is flowing through R2. Okay, let's look at this. So there are two resistors in series, and since the current measures the rate of flow of charge, the same current I flows through R1 and R2 if they are connected through the same cell. Now potential difference, if you look at the potential difference, this overall potential difference has to be equal to the potential drop across R1 plus the potential drop across R2. So the potential drop across R1 is I R1 according to Ohm's law, and the potential drop across R2 is I R2 according to Ohm's law. Now the total potential difference across the combination equal to V1 plus V2. Now we know the equation for V1, which is I R1, and we know the equation for V2 I R2. Let's take I outside. Then we will get V equal to I multiplied by R1 plus R2. Now let's bring this I to the left hand side. Then we get R equivalent, that is the equivalent resistance of this whole combination is R equivalent, which is equal to overall voltage, that is potential difference divided by the current. So V by I equal to R1 plus R2 from this equation. Now we have R equivalent equal to R1 plus R2. So what does this tell you is, when you have resistors in series combination, you just have to add all of them to find the equivalent combination. So now if you have 3 resistors in a series connection, then you do the same calculation, then you will end up here with V equal to I multiplied by R1 plus R2 plus R3. So now if you have n number of resistors in series, then the equivalent resistor is supposed to be R1 plus R2 plus etc. up to Rn. So in series combination, you just have to keep adding the resistors. So that is the conclusion of this. Now let's go to parallel combination. So in parallel combination, what we do, we connect one ends of the resistors to one point and the other ends to one point. So this is different than the series combination. So in parallel combination, you see the currents are not supposed to be equal. See, there is a current I coming in, but when the charges come to this junction, they have 3 choices. They can go through this, they can go through this, they can go through this path. And how the charges go is decided by the resistance values here. So the current I is divided into 3 parts here, I1, I2 and I3. And there is a potential difference V across these 3 resistors, which is the constant for all the 3 resistors. So we are going to use this concepts, find out what is the parallel combination of resistor, what is the equivalent resistor in parallel combination, we are going to find out. So there are 2 resistors R1 and R2 in parallel connection. So the total current is given by I equal to I1 plus I2. And we know that the potential difference is same in both the cases. So we now have V equal to I1 R1. So the potential drop across resistors R1 is equal to I1 R1. Potential drop across resistance R2 is equal to I2 R2. So now we know that I total current is equal to I1 plus I2, and we will rearrange this equation and substitute here. So I1 equal to V by R1 plus I2 equal to V by R2. So let's take V to the left hand side, and if you take this to the left hand side, then what will you get? I by V. So I by V equal to 1 by R1 plus 1 by R2. Now let's assume that R equivalent is the resistance of this whole combination. Now we get I equal to I1 plus I2. Yeah, if you take this V to the left hand side, then what you get? I equal to V by RQ according to Ohm's law, right? According to Ohm's law, I is just the current and V is the overall potential and R equivalent is the equivalent resistor. So from this what we get, if you compare this equation and this equation, we get 1 by R equivalent equal to 1 by R1 plus 1 by R2. So in a parallel combination, if you want to find the equivalent resistor, you have to take the inverse of the resistance and add them and then take the inverse, then you will get the R equivalent. So if you have n number of resistors in parallel, then the overall 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus etc. up to 1 by Rn. Okay, now we talked about series combination and parallel combination, but now you are given a circuit like this. It's a very simple circuit, but it has both series connection and parallel connection. So you have these 2 resistors R2 and R3 in parallel combination, and this equivalent resistor is in series combination with R1. So how do you simplify in this case? So whenever you are simplifying a circuit, first look for this parallel combination and then simplify this, and whatever equivalent you are getting, that you put as a R equivalent with the series combination here with the R1. So let's see how to do this. So first let's find out the R equivalent of this parallel combination. So 1 by R equivalent to 3. 3 represents equivalent of these 2 equal to 1 by R2 plus 1 by R3. So let's simplify this further. Then we just cross multiply here. So R3 plus R2 divided by R2 R3 and take the inverse of this to find R equivalent, then you get R2 R3 divided by R2 plus R3. Now this equivalent resistor is kept here as a series resistor with R1. So now R1 is there and R equivalent is substituted here. So we are substituting this parallel combination with this one single resistor with value this given by this equation. So first we have to find out what is R equivalent to 3 and substitute it here. Now it becomes easy because in series combination we just have to add the resistance values. So in series combination now the equivalent of 1, 2, 3 resistor equal to R1 plus R equivalent of 2, 3. So then we get this. And how do we find the overall current in the circuit? Now we know the equivalent resistor. Now divide this by divide the voltage by this resistance, then we get current. So according to Ohm's law, I equal to V by R. Instead of R, we have this R equivalent, which is given by this plus R1. So if you have R1 plus R2 R3 divided by R2 plus R3, this is the equivalent resistor. So V divided by this value gives the current. So whenever you are given a circuit with the combinations in series and in parallel, you have to simplify this step by step and go to the next equivalent circuit and finally get the overall equivalent resistor and use Ohm's law to find the current. Okay. So okay, we have talked about series and parallel combination. Now we are going to the cells. So cells means batteries which produce the electricity. So which helps us drive the electricity through the conductors, right? So this is a typical cell which has electrodes, one positive electrode and one negative electrode. So let's consider a point A in the positive electrode and point B in the negative electrode. And we are connecting this with a resistor external load, and there is a current I passing through this, and this is the electrolyte. The electrolyte is just connecting the electrodes. So any cell will have two electrodes and in between an electrolyte so that the ions can move within the cell. So this is the structure of a cell, and this is just a symbol which represents the same circuit. This symbol represents the cell and this is just the R which is given here. Now, the potential difference between positive and negative electrode is, if we assume that the P is at V plus potential and N is at minus V minus potential, if you want to find the potential difference between these 2 points, then you get V plus minus of minus V minus. So the potential difference becomes V plus plus V minus. So this this cell is capable of giving this much potential difference. So if you connect something across this, you can drive this much potential difference from the cell. So this difference is called electromotive force of the cell and is denoted by epsilon. So epsilon equal to V plus plus V minus, and it is greater than 0. Now we are connecting a resistor R across this cell. A current I flows across R from C to D. Now there is a current flowing from C to D. So there will be a voltage potential across this R which is denoted as V. Now a steady current is maintained because current flows from N to P through the electrolyte. Okay. Now the current is flowing from P to N outside the cell. So current is flowing through this way. But if you want to maintain the steady current, then the current has to go from N to P like this inside the electrolyte. So this is how the whole circuit is completed. So inside the electrolyte or a cell, through the electrolyte, the current flows from N to P within the cell. So the electrolyte through which a current flows has a finite resistance, because we already talked about resistance in conductors. So how this outside circle has a resistance R, capital R. Similarly, the electrolyte also has a resistance which is called internal resistance and denoted by small r. Now if you look at the voltage drop across this R, that is capital V, which is equal to epsilon minus I multiplied by R. So epsilon is the potential difference minus there is already a potential drop across this A and B because of the internal resistance which is given by I into R. So this is the equation V equal to epsilon minus IR. So this EMF is the potential difference between the positive and negative electrodes in an open circuit when no current is flowing through the cell. So what do they mean by this? If the internal current is 0, that means I equals to 0, then what is the condition? V becomes epsilon. So we get exactly the electromotive force of the cell as the potential difference only when there is no current flows through the circuit. But if there is a current flows through the electrolyte, then we have R here, small r here. So we get always less than epsilon for V. So EMF is the potential difference. That means epsilon equals to V only when I becomes 0. From this equation, it's clear. Now, internal resistance of cells in the circuit may be neglected when the current I is such that epsilon is much greater than IR. So in this case, we know V equal to epsilon minus IR. When epsilon is much bigger than this product IR, we can assume that V is approximately equal to epsilon. So we can ignore this internal resistance. V is the potential difference across the resistor R. So V can be expressed as from Ohm's law. If I is the current that is flowing through R, then V equal to I multiplied by R. So let's substitute instead of V, I multiplied by R. Then by rearrange this equation, we get I equal to epsilon divided by R plus R. So how do we do that? We take this IR to the left hand side and take I common, then take R plus R to the denominator to the right hand side. So what does this equation tell you? I is the current that is drawn from the cell, which is equal to epsilon divided by R plus R. So if you have a cell which has an internal resistance small r and you connect an external resistance capital R, the current that is flowing through the circuit can be calculated by dividing the epsilon, that is the electromotive force of the cell, by the sum of both resistance. So even internal resistance plays a role in deciding how much current you get from the cell. So the maximum current that can be drawn from a cell is for R, capital R equal to 0. That means the external resistance, when external resistance is 0, that means you get the maximum I maximum equal to epsilon divided by small r. So that was about the cell EMF and internal resistance. Now just like how we did with the resistance, we will do the same thing with the cells. We will add the cells in series and in parallel and see what happens to the equivalent potential. So the EMF of two cells, epsilon 1 and epsilon 2, and the internal resistances are R1 and R2 respectively, and we are going to connect them in series like this. So when you connect the cells in series, you add the negative of one cell to the positive of the other cell, and this is called a series combination. So when you have V of AB, V of A minus V of B, that is, let's calculate the potential difference across this particular cell. So that is supposed to be V, right? We already talked about this equation, V equal to epsilon minus IR. So V across this particular cell, VAB, is going to be VA minus VB, which is equal to epsilon 1 minus IR1. In this also it is noted that the I has to be same through these two cells because they have the same series connection. So according to the conservation of charge, the I has to be same. So now V of AB equal to V of A minus V of B, which is equal to epsilon 1 minus IR1. Similarly, V of B minus V of C equal to epsilon 2 minus IR2. Now if I want to find out what is VAC, I have to do VA minus VC, right? So I can add plus or minus V of B here. So if I add minus VB plus VB with this equation, then I get VA minus VB plus VB minus VC, which is nothing but these two equations. Then let's substitute these two equations here and let's take the terms with epsilon together and let's combine the terms with I together. Now we get VAC equal to epsilon 1 plus epsilon 2 minus I multiplied by R1 plus R2. So if you look at this equation, this is similar to V equal to epsilon minus IR. But in this case, instead of epsilon, you have epsilon 1 plus epsilon 2. Instead of R, you have R1 plus R2. Now, we can replace these two cells in series with a single equivalent cell like this. So let's consider that both of these cells produce an equivalent EMF epsilon equivalent and they produce an equivalent internal resistance as R equivalent. So if you combine these two equations, compare these two equations, then you get epsilon equivalent equal to epsilon 1 plus epsilon 2, R equivalent equal to R1 plus R2. So this is the equivalent result of having two cells in series combination. So if you have two cells in series combination in this way, then you add the EMF to get the equivalent EMF. and you add the internal resistance R1 plus R2. Now if one of these cells is connected in a reverse way, for example, if the negative of this cell is connected to the negative of this cell, let's say if we invert this cell, then we just have to substitute here epsilon 1 minus epsilon 2. Okay, but internal resistance will be added, but we can say in epsilon 1 minus epsilon 2 if you reverse the connection like this. Okay, so this is what we derived in the previous slides. So the equivalent EMF of a series combination of n cells is just the sum of the individual EMFs. The equivalent internal resistance of a series combination of n cells is just the sum of the internal resistances. Now let's go to the parallel combination, just like we did with the resistors. So the cells are connected in parallel. The current I1 and I2 flows through each cell respectively. The total current is I, which is equal to I1 plus I2. So the potential difference across the terminals is, now the current is different but the potential has to be same across these terminals B1 and B2. So let's take the potential difference across the terminal AC as V, which is equal to VB1 minus VB2, which is equal to epsilon 1 minus I1 small r1 in this case. In this case it's supposed to be epsilon 2 minus I2 into R2. Now we know that the total current I equal to I1 plus I2. So I1 plus I2 equal to, we can derive I1 from this equation, which is epsilon 1 minus V divided by R1. If you just take this I1 to the left hand side and V to the right hand side and divide it by R1, then you get I1 here. Similarly, I2 equal to, from this equation, epsilon 2 minus V divided by R1. So we just combine the terms with epsilon and V. What do we get here? Epsilon 1 by R1 plus epsilon 2 by R2 minus V multiplied by 1 by R1 plus 1 by R2. So from this equation, again let's simplify it a little bit further. So from this equation, we will just cross multiply and simplify this. So epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 minus I into R1 R2 by R1 plus R2. So V is equal to this. And the potential difference across the terminal can also be given as epsilon minus IR equivalent. This is from the equation B equal to epsilon minus IR. Now if you compare this equation with this equation, epsilon equivalent is nothing but this whole term and R equivalent is nothing but this whole term. So if you simplify this epsilon equivalent equal to this, we can simplify this further like this. And R equivalent, if you simplify this, then you get 1 by R equivalent equal to 1 by R1 plus 1 by R2. And if you divide this epsilon equivalent by R equivalent, then you can get this. So what we get from this is how to find out the R equivalent. So 1 by R equivalent is given by 1 by R1 plus 1 by R2, etc. up to Rn. Similarly, epsilon equivalent divided by R equivalent is given by epsilon 1 by R equivalent, R1 plus etc. up to epsilon n by Rn. So this is what happens in a parallel combination when you have many different cells with different EMFs. Okay. Now we have come to the important rules which help us work with the circuits. See, we already learnt about how to deal with resistors in series, resistors in parallel, cells in series and cells in parallel. But those are not enough to solve complex electric circuits. So we need these rules called Kirchhoff's rules when we come across circuits like this, where these Kirchhoff rules give us easy ways to solve these circuits. So there are two rules. The first rule is called a junction rule. At any junction, the sum of the currents entering the junction is equal to the sum of the currents that leaving the junction. So what do we mean by junction? So from this particular circuit, we can say A is a junction because there are many connections going from this. So just like a road, a junction where there are so many roads that are meeting at a point, we can call this as a junction, this as a junction. So if you look at the junction, any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. So in this particular case, if you look at A, the current that is entering A is I3. So let's take I3 equal to the currents that are leaving this junction is I1 and I2. So I3 equal to I1 plus I2. This is just an example for this particular rule. So why is it so? It is again about conservation of charges. So if, for example, 10 charges come here per second, they have to be divided by these two branches. There is no other way to go for the charges, right? So if 10 charges are coming in, those 10 charges have to be divided between this I1 and I2. For example, 5 can go here, 5 can go here, or 4 can go, 6 can go. But whatever comes in have to go only within these two streams. That's why there is this junction rule. So the sum of the currents coming has to be equal to the sum of the currents going from the junction. So when currents are steady, there is no accumulation of charges at any junction. So this is given that the charges don't stay at this junction, they always leave. There is no accumulation of charges. Thus, the total current flowing in must equal the total current flowing out. The next rule which we are going to see in Kirchhoff's rule is a loop rule. So when we say junction, this is a junction. We already talked about this. But what is a loop? Loop is a closed circuit like this. For example, this particular circuit has two loops. One is the upper loop here and the other one is the bottom loop here. So the algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. So if you take any loop, the potential difference has to be 0. If, for example, the electric potential is dependent on the location of the point. So the starting with any point, if we come back to the same point, the total change must be 0. For example, I am starting from here. So I am going through this and going through this and going through this and going here, going here, going here, and coming back to the same point A. And we know that the potential difference depends only on the position and not on the way we take. So we talked about this in the previous chapters. So it is a conservative force, right? So it depends only on the positions. So you start at a point and come back to the same point, the total potential difference is going to be 0. That's what this rule says. So the algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. So the electric potential is dependent on the location. So the starting with any point, if we come back to the same point, the total change must be 0. So let's just use these rules here. So at a junction A, the current leaving is I1 plus I2, the current entering is I3. So according to the junction rule, I3 equal to I1 plus I2. We talked about this already. So now we are going to apply the loops rule for this particular circuit. So let's take the loop AHDCBA. AHDCBA. So this upper loop. So if you take AHDCBA loop, it gives you, there is a potential drop of minus 30 into I1 because it is I multiplied by R as given by the Ohm's law. So the potential drop here is going to be minus 30 I1, and when the current comes here, there is this 45. So we have a plus 45 here, and minus the total resistance of these two is 41, and the current that is flowing here is I3. So I3 multiplied by 41, which is equal to 0. So the sum of the potential drops have to be equal to 0 in a closed loop. And similarly, if we apply the same thing to the loop AHDEFGA, AHDEFGA. So we will take this full loop. So let's do the same thing again. So we have minus 30I, and then we come here and here. These two are in series combination. So we have 20 plus 1, 21 ohm resistor, where I2 is the only current flowing. And since I2 is going in the opposite direction compared to I1, we have added a plus here, where we have added a minus here for I1. So it is plus 21 I2 minus 80. Why it is a minus? Because the positive is facing this way, so there is minus 80. So these two rules are very important when solving any circuit. So far, whenever we have a complex circuit, there are different things which we learned which will help. One is resistors in series and parallel, cells in series and parallel, and junction rule and the loop rule. Okay. Now let's look at this Wheatstone bridge. So this Wheatstone bridge is a direct application of Kirchhoff's rule, and it is very helpful in finding unknown resistances. We will see how it is applied to find out what is the unknown resistance. So the structure looks like this. There are 4 resistances, R1, R2, R3, R4, and they are made in this way, where there is a junction A left side, which is connected to a cell here, to the C, and the junctions B and D are connected to a galvanometer. So what is a galvanometer? It is a device to measure the flow of current. So there will be a needle inside this galvanometer. It will show a deflection only when there is current flowing. If there is no current, the galvanometer deflection will be at 0. So let's see what's there. So Wheatstone bridge is an application of Kirchhoff's rule. The bridge has 4 resistors as shown in the figure. There is a galvanometer connecting the junctions B and D. So it is assumed that cell has no internal resistance. So now for simplicity, we will assume that epsilon has no internal resistance. We will ignore this. So in general, there will be current flowing through all the resistors, right? But if the current Ig is equal to 0, Ig is the current that is flowing through the galvanometer. If it is 0, then it is called the bridge is balanced. So when will the bridge be balanced? We will see. So this is called a balance condition when Ig equal to 0. That means there is no current flowing through the galvanometer. So let's apply the junction rule to B and D. So let's take the junction B and let's take the junction D when Ig equal to 0. So there is no current flowing through the galvanometer. So whatever current comes into B has to be equal to the current that goes out of B, right? So that is why I2 equal to I4, because there will be another current flowing here, but we know that galvanometer current is 0. So when this condition is satisfied, I2 equal to I4. Similarly, when this condition is satisfied, I1 that is coming into D equal to I3 that is going out of D. This is just applying junctions rule. And so these two conditions are gathered now. And now let's apply a loop rule to this circuit. Let's take the loop ADBA. Where is ADBA? ADBA. So the left triangle ADBA. So if you take ADBA and calculate all the potential differences, first we have I1 here. So we will take this direction as negative. So minus I1 R1, and Ig is 0. So we are having a 0 here. And here it is plus because it is in the opposite direction. So I2 R2 equal to 0. Similarly, if you take the loop CBDC, we will do the same thing. So here I2 R4 plus I2 R4. So this is I2 R4. Why we are saying I2 instead of I4 from this equation? So we have I2 R4 plus 0 minus I1 R3. Instead of I3, we have written I1 here from this equation. So I1 R3 equal to 0. So look at this equation. I1 R1 equal to I2 R2. If you rearrange this, it says I1 R1 equal to I2 R2. So we can take i's in the left hand side. So I1 by I2 equal to R2 by R1. So let's keep this aside. Now let's look at this equation. So I2 R4 equal to, if you take this to the right hand side, I1 R3. Right? So then if you divide I1 by I2, then you get R4 by R3. So these two equations are same. I1 I2 equal to I1 by I2 equal to R2 by R1, I1 by I2 equal to R4 by R3. So we can equate these two equations, right? So we can combine these two equations, and what we will get is R2 by R1 equal to R4 by R3. So this is a really beautiful equation, because when you have a balance condition, that means when Ig equals to 0, the resistance at this left side equal the ratio of resistance at this left side equals the ratio of resistance on the right side. So if, for example, these two are fixed, this condition is called a balance condition, and this is valid only when Ig equals to 0. This is a very important point. Only when Ig is equal to 0, this condition is satisfied. So this is called a balance condition. So now let's say that I don't know what is the resistance value for I4, and we need two resistances which are already known. So R1 and R2 values are already known, and we have R3 which is variable resistance, right? So what we can do is we can establish this circuit, and we can keep changing R3 until Ig becomes 0. When Ig becomes 0, then we know that this condition has to be satisfied, R2 by R1 equal to R4 by R3. So two known resistances are used, R2 and R1. The variable resistance R3 is varied until the balance condition is achieved. So until Ig becomes 0. Now the unknown resistance R4 can be calculated by bringing this R3 to the left hand side. So R4 you have R3 multiplied by R2 by R1. This R2 and R1 are fixed and R3 is a variable resistance. So for what value of R3 you achieve the balance condition, that value will give you the value of R4. So this is a very useful circuit which allows us to find the unknown resistance by using the known resistance and a variable resistance and by using the junction and loop rule. Okay, meter bridge is now a variation of the Wheatstone bridge. And if you look at the meter bridge, it is similar to the Wheatstone bridge. But in this case, instead of 4 resistors, now we have 2 resistors and 1 meter scale. This is 1 meter long wire. We have a movable point here, movable jockey. So we keep moving this. There is a galvanometer here. What we do normally is we begin at one end. We keep moving this this point along this wire, and at some particular point the galvanometer becomes 0, and we note down the length at which the galvanometer becomes 0. Right? So now we are going to derive. This also serves the same purpose. We can find out the unknown resistance R, and this is exactly like the Wheatstone bridge. So we can modify this equation R2 by R1 equal to R4 by R3 to this by using R2 as R, that is the fixed resistance here, and R1 is S, the fixed resistance here. R4 and R3 are now, see, if you know RCM, that is the resistance per unit length, then RCM multiplied by L1, that is the length of this part is L1, multiplied by RCM will give you the resistance of this length L1, right? Then RCM multiplied by 100 minus L1 will give you the remaining resistance. So then R4 and R3 are replaced by RCM L1 by RCM 100 minus L1. So if you simplify this, RCM gets cancelled. So you get L1 by 100 minus L1. So the beauty of this is you can calculate the unknown resistance just by measuring the length. You don't even have the resistance on, you don't even need to know the RCM here. That is, whatever wire you are using, you don't need to know how much is the resistance per unit length. But just by measuring at what length L1 the galvanometer becomes 0. So at what length L1 the balance condition is achieved. By using this you can find out what is the unknown resistance R equal to S multiplied by L1 divided by 100 minus L1. Okay. So we have come to the final part of this. So this is called a potentiometer. So this is also similar to the previous cases, Wheatstone bridge and meter bridge. So we are going to use this to compare the cells. So for example, we have two cells with two EMFs, epsilon 1 and epsilon 2. We want to compare their values. How do we do that? So we have a potentiometer. A long piece of uniform wire is cut in several pieces, placed side by side and connected at the ends by thick metal strip. So these are the thick metal strips. So this is the wire, A to C is the wire. We have cut that wire in several pieces and we have made a circuit like this with a battery with a variable resistance here, and this is just a key. So from A we have two connections. So there is a switch here. So switch means we can connect 1 to 3 or we can connect 2 to 3. So we can do both of these things. A current I flows through the wire which can be varied by a variable resistance in the circuit. So variable resistance is this. This resistance controls how much current flows through this wire. Since the wire is uniform, the potential difference between A and at any point at a distance L from A is epsilon of L equal to phi into L. So phi is the potential drop per unit length. See, if potential drop per unit length is phi, then for L1 L length, then the total potential drop is going to be phi into L. So the EMF of two cells can be compared using the potentiometer. So here also we have a galvanometer. So we need to look at, first we need to connect this 1 to 3 so that we are working with epsilon 1 here, and we have to keep moving this point from this A towards C, and we need to see at what point the Ig becomes 0, the galvanometer becomes 0, and we need to note down the length of it. And we need to connect this 2 to 3, again repeat the same thing and note down what is L2. So that's what we have to do. The jockey is moved along the wire till at a point N1 at a distance L1 from A. There is no deflection in the galvanometer. Applying Kirchhoff's loop rule to the closed loop, AN1 G31A gives AN1 G31A. So this is the circuit AN1 G31A. So this circuit gives us phi L1, that is the potential drop across this length, plus 0 because Ig is 0 here, minus epsilon 1 equal to 0. Similarly, if you do the same thing with AN2 and G32A. So if you do the same thing, then you get phi L2 plus 0 minus epsilon 2 equal to 0. So if you rearrange this equation, then you get phi L1 equal to epsilon 1, or you can say phi equal to epsilon 1 by L1. Similarly, you will get phi equal to epsilon 2 by L2. If you equate this, then you get epsilon 1 by epsilon 2 equal to L1 by L2. So just by looking at the length of the wire where the Ig becomes 0 when that particular cell is connected, that is L1, you can compare the values of EMF of two cells. So that is the role of a potentiometer. Okay, now what if you don't know what is the value of epsilon, or okay, you know the value of epsilon but you want to find out what is the value of internal resistance. So what you can do is you can take one epsilon, you can remove one epsilon and replace it by a resistance box. So maybe variable resistance you can keep there. So now the potentiometer can be used to measure the internal resistance of a cell. For this, the cell whose internal resistance is to be determined is connected across a resistance box through a key K2 as shown in the figure. With key K2 open, balance is obtained at length L1. So let's remove this key 2. So this is open, so there is no current flowing through this circuit. Then we have this loop AN1G epsilon A. So if you look at this, then you have this equation since Ig equals to 0, epsilon equals to phi into L1. Now let's close this K2. The cell sends a current I through the resistance box R. If V is the terminal potential difference of the cell and the balance is obtained at the length L2, then now we have this condition V, that is the potential drop, equals to phi into L2. So if you do epsilon by V, then you get phi get cancelled, you get L1 by L2, right? And now you know that epsilon equal to I into R plus R and V equal to I into R. So if you divide epsilon by V, substitute these two equations in this, then I gets cancelled, then you get R plus R divided by R. So epsilon by R equal to R plus R divided by R, which is also equal to L1 by L2. So R plus R divided by R equal to L1 plus L2. So now if you rearrange this equation, then you can find the internal resistance R equals to capital R multiplied by L1 by L2 minus R. So what we did here is, so we connected epsilon and found out what is L1, and then we connected this key, this resistance box, and found out what is L2. Just by measuring these lengths and the known resistance value R, we can calculate what is the internal resistance of this cell. So this is how we use this loop rule to find out what is the internal resistance of a cell. Thank you.
Why waste time in commute and spend a lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.